Now it's time to consider what happens when we connect 1-bit full adders together. So we're going to first of all consider a 4-bit adder. We're going to add the numbers 0111 and 0001. Let me just, as an aside here, say that 0111, well, that's the number 7, and 0001, that's the number 1. So when I'm adding them together, I expect to get an 8, and an 8 in decimal is 1000 in binary. So I pretty much know what the answer is supposed to be, but let's double check that we get what we expect. It says no carry in to the least significant bit, so I know that this is going to be a 0. Let me go ahead and copy the values of A. A3 is going to be the most significant bit, A2, A1, and A0, and then B3 is going to be the most significant bit, 0, 0, and 1. Okay, looking now strictly at the least significant bit, I have A0 plus B0 plus C0. That's the carry in to the least significant bit. So we have 1 plus 1 plus 0. Well, that'll be 2, and a 2 is going to be a sum of 0 and a carry out of 1. Then in the next bit, or in the next bit slice, so now I'm looking at 1, so that's this 1 right here, plus 0 plus 1, and once again that's going to yield a 2, which is a sum of 0 and a carry out of 1. In the next bit, 1 plus 0 plus 1 is going to give me a 2. Again, that's going to be a sum of 0 and a carry out of 1. And then in the most significant bit, I have 0 plus 0 plus 1, which gives me a 1 for the sum and a carry out of 0. And I get exactly what I expected. 1, there's 1, 0, 0, 0. And the carry out says that if we were to drive this on to another result, there would be nothing to carry into the next result. Okay, please draw an 8-bit ripple carry adder. Okay, so this isn't too bad. I need to start off with 8 boxes. Let's hope I can space these out well. Okay, mission accomplished. And then I know that I'm going to have a carry in to the least significant bit. I know that every one of these is going to have a bit of A and a bit of B. It's going to get a little bit tedious. Feel free to fast forward if you want to. I wish I could fast forward. Okay, and then we know that there's going to be a sum coming out of each one of these. So this is going to be, we have S0, we have S1, we have S2, S3, S4, S5, S6, and S7. Now so far what we've really done is we've shown 8 independent 1-bit full adders. And you might say, well, what is it that makes the connection from 1-bit full adders to the 8-bit full adder? It is that the carry out from 1 bit goes in to the carry in of the next bit, and that would be C1. Now I kind of like to show it coming out the bottom of 1 and then scrolling back up to the top of the next one. That's of course different than what this picture was. I didn't draw that picture, but I am drawing this picture, so I'm going to show them the way that I like to show them. So it's coming out the bottom, coming in on the top. Coming out the bottom, coming in on the top. Out, in, out, in, out, in, and out, in. And then of course we can label this. We'll have C2, C3, C4, C5, and C6, and C7. And then we can have, I'll do it the way that I like to do it, which is I'll have it coming out the bottom, and maybe I'll go ahead and route that somewhere else. So I'll just have it go out here, just in case we need to have an output from that last bit. So we end up with an 8-bit ripple carry. Now the thing to remember about the 8-bit ripple carry is that you can't perform the calculation of any one bit until all the bits before it have completed their calculation. So when C0 flows in on the right, you have to complete the work of the first adder before you can complete the work of the second, and then the third, and then the fourth, fifth, sixth, seventh, and eighth. They're going to occur one at a time, sequentially, and only when they're all done will you have the final result. And that's really highlighted by this question. If each 1-bit full adder requires 1 nanosecond to perform its calculations, how long will a 32-bit ripple carry adder take to perform its calculations? Well, if there are 32 of them, this is not a super hard calculation. If there are 32 and each one requires 1 nanosecond, then the total amount of time it's going to take is 32 nanoseconds. And that is the answer. That's the answer to the question that was being asked. But let me just show you, go one step further. If I say that the frequency with which we can clock this device is controlled by that adder, then that would be 1 over the period. And 1 over 1 nanosecond is going to be 1 gigahertz. Now, if you went into Best Buy or somewhere and wanted to buy a computer, you'd probably expect a little bit better than 1 gigahertz, but it's in the ballpark. Maybe you'd hope to have maybe 7 or 8 gigahertz, 5 or 6, something like that. But 1 gigahertz is in the right ballpark. Let's consider, though, what happens if this is F1. F2 is going to be 1 over the second period, which is now 1 over 32 nanoseconds. And it turns out that that is 31.25 megahertz. And that is not acceptable. If you had a computer that was designed with an arithmetic logic unit that had ripple carry, you would never sell a single computer. Ripple carry is a great thing to learn the very first time you're studying addition. But in reality, ripple carry is not the way that it's done. There are other methods, look-ahead carry, fast carry. There are other ways that you can do this carry operation that you're going to study next year. But for right now, ripple carry is a good first method because it does, in fact, give the correct result.